So welcome to lecture 32 of MCS 472. So this is a lecture where we start a new chapter on partial differential equations. We will derive three equations, mainly to solve the air quality modeling problem. So we will first do this without diffusion, and then we will add diffusion to it. So we will have three partial differential equations: the advection equation or the transport equation. Then we have the diffusion equation or the heat equation. And we will end with the advection diffusion equation. So the purpose of this lecture is to introduce these three different types or but very related types of partial differential equations. We will also introduce some notation, and there will be exercises, of course, but at the end of the lecture there will be three proposals of topics. So partial differential equations are extremely useful in modeling and solving problems. So let's consider a problem here. What is the setting? So we are considering the air quality, and the air quality is in general good, except that there is an industrial plant, unfortunately not that far away or not that close either from our house. There are these fumes that get emitted once an hour, and what happens if to the air quality around in the house when the wind is blowing in the wrong direction or in the direction away from the plant towards our house. And in particular, the problem is how can we understand the concentration of these fumes. So much of this lecture is based on another industrial mathematics textbook. So this book starts very early on with differential equations. So in our approach, so this is already chapter 2 in that book. We started a little bit slower. Okay, what can we expect? Well, if we had to make a picture, so here is a plausible scenario. We have we put the plant, the origin or the smokestack at position 0, and there is the assumption so that there is this diffusion, so that there is this profile of the fumes. So initially the concentration is mainly at x equals 0, so when the emission for a couple of minutes happens, but then after time elapses the concentration kind of declines. So this is the pattern if there is, for example, no wind. So what do we have? So we have a concentration. So C is for concentration. So we have a given profile. So here I just plotted a bell-shaped curve. And we have, so the profile is just a function, the bell-shaped curve, but then there is the profile of this function as time evolves. So we will be looking for a function in two variables. So this is where the difference with the ordinary differential equations arises. So we have two independent variables, space and time. Space typically x, time typically t. Okay, so that is the problem. What is the evolution of the fume profile? So here is a solution. So assuming that the wind is blowing at constant speed, then speed multiplied by time equals distance traveled. So the distance that is then traveled is v times t, and we have the initial profile, and we subtract the distance traveled from the original location x. And why is that? Because the fumes shift actually in the opposite direction of the wind. Therefore, we have the minus signs. Okay, so that's our solution. What's now the equation? So we start working backwards. So let's try to look at the derivatives with respect to the two independent variables. So we take the derivative with respect to space and the derivative with respect to time. You see the minus v comes in there, so we applying the chain rule to our profile function, to the solution. And we can see that we can, so this is the whole point of the differentiation and of the differential equation. We actually have now an equation that doesn't have this proposed solution in it anymore. So the proposed solution is a probable solution, but when we eliminate it, we arrive at what is called the advection equation. So it's an equation that is first order in both time and the space, just like with the differential equations. When we have a first order differential equation, then we need to find an initial condition to have a unique solution, and the initial condition is given by the original profile of the fumes. Okay, so this is our first differential equation, so it's a very simple one, but it's a good place to start here. So let's start to look at this equation. The equation, the partial differential equation that we just arrived, has also many other applications. In particular, it's known as the transport equation. So I should say that the advection equation in terms of for the air quality is actually not a good equation because there is no diffusion. So it's actually really, really bad that the concentration at the smokestack and at your house will be the same if you will apply this equation. So not a good model, not a good situation. But it's a good situation if you consider traffic. So we have the traffic concentration, the number of vehicles per mile. And we want to see the evolution of this concentration. So how many vehicles are concentrated at a location at some time. Now you see actually that the constant speed, if you drive a car, then actually you know that the constant speed is also not really a realistic model. So the advantage of going to the transport equation is that we will forget about the diffusion for a minute, but we will do something about the constant speed, because that's actually also the wind can change, is typically never constant. Okay, so here is the traffic flow, traffic concentration, where it makes sense to relate the speed of the cars with the concentration. So I said that the constant speed is not realistic, but actually it is if you consider the traffic when there is no when there's almost no cars on when there are no cars on the road, then everybody drives at the speed limit. So that's quite a, a realistic phenomena. So we have the interpolation here. So we have the speed. The picture shows the free traffic speed on the vertical axis here. So that's the maximal speed. And as the concentration increases, more and more cars come at the road, the speed has to decrease. So we actually studied, we mentioned this a little bit with the 3-second rule. And there was also a project that was related to that. So we have the free traffic speed and we have the jam density. So the speed drops to zero when there are simply too many cars on the roads. When that density is accomplished, there is no more traffic speed. Okay, so we have this model now. So how does this change now our equation? Well, instead of putting the v as a constant, we now actually have v related to the concentration. So we still have the proposed solution in mind with the initial concentration. So pulling the variable speed into the derivative with respect to x corresponds with this term still with the proposed solution. So at time equals 0, there is this initial concentration. Okay, so this is the modified transport equation, and we will solve that equation, or we will use that equation in a later lecture. So this to indicate that this very simple first partial differential equation that we derived is already not at all useless. Okay, but I want to get to diffusion, so let's now, let's first look at an exercise. So this exercise is kind of useful to consider the connection with ordinary differential equations. So consider here this initial value problem. So the f of x can, for example, be x, then you have the exponential as the solution. So we have solved already many differential equations in numerical analysis, and we had an entire chapter on ordinary differential equations. So the solution of this initial value problem is geometrically a curve that passes through this x naught. So we can actually write the solution now also as a function into variables. So often the first thing that people do when they have a new problem, a partial differential equation is a new problem, they try to reduce it to a problem they can solve already. So often one classical method to solve a partial differential equation is to reduce it to solving many ordinary differential equations. So that's one of the techniques. This exercise is kind of suggestive to this. So you can actually see the initial value problem where the initial condition, so the initial position at time 0, is actually a second parameter, is also a variable. So now we actually do have a two variable problem. And the solution is actually differentiable also with respect to that second variable. So we have the first variable, which is time still. The second variable is now our initial position. Show that you have this partial differential equation. So you have at the left the derivative with respect to time, and at the right you have the derivative with respect to space. So there is a showing that needs to be done. So you can say alternatively a proof You will get already credit if you understand the setting up for this problem. Take, for example, f(x) to be x and with the exponential. So you can verify for these particular f, or you can take a polynomial, verify it for any polynomial, for example. That is also good work. So these are continuously differential functions. Okay, let's now, before we get into diffusion, let's see how we can push this further. So when we have done something, we can always try to ask, can we do something more? Can we generalize what we've just did? Well, yes, we can. We can move to 3 dimensions, and for that the operators, working with operators is very useful. So we have a concentration now. So we were looking at a 1-dimensional problem, but this problem, the concentration is defined in 3 variables. Actually, the four variables. Time is the fourth one. So we are working in 4 dimensions. We have the velocity vector, which is here written from multivariate calculus with the quaternion notation. With this quaternion notation, we define the del operator. And with this operator, we can generalize the advection equation to 3 dimensions. So here is the 3-dimensional formulation. So it's formulated very compactly. So we have our vector v, the velocity vector. We have the concentration c in 4 variables, the 3 space variables, and then time. The derivative with respect to t remains the same. What is different is that instead of the derivative with respect to x, we have the del operator. That is dotted with the velocity concentration vector. So here I have illustrated the dot product on a velocity vector, but we apply this in the 3-dimensional advection equation to the velocity vector multiplied with the components. Good. So this is the 3-dimensional problem. Here is a profile for the fumes. So I got this from this chapter 2 of the Friedman-Littmann book. So we can work with these bell-shaped functions, but you can also work with a cosine, where you have what is called a cosine hill here. Cosines, it will turn out appear very natural when we consider the heat equation, the diffusion equation. So we have a radius. So again, depending on the initial profile here, you can make this very small, where you have then a profile that is very tall. So the cosine, I must say, has another benefit, that you have numbers between bounded numbers between -1 and 1. We multiply here with pi over 4 the radius. So we are looking at the cosine between so we should actually say that we have the center of the smokestack, x0, y0. The r function models the radius, and that radius, which is essentially the square root, the distance from the smokestack. So here you can model initially the initial concentration, how far, what is the radius where you notice it when the emission of the fume happens. So there are these parameters that you can get. So there is this parameter 4, then there's also the parameter 50. So that is a model, a multi-dimensional model that gives you the concentration at any spot. Again, this is a 2-dimensional model. no, it's a three-dimensional model. So the height is actually the no, it's, I'm sorry, it is at any two-dimensional point. It gives you, and that's quite a realistic model. It gives you the concentration of the fumes. All right, second part. So our advection equation was actually not very useful, or actually pretty bad if you use that. If the wind blows in the wrong direction towards your house, you're going to be in trouble. So you're going to have the same concentration as the smokestack, which is very pessimistic. So this would simply assume that there is no diffusion. Okay, so we want something like this. So what is diffusion? Diffusion is the transition from a high concentration to low concentration. So the profile at the beginning of time is very highly concentrated at the origin, which is the location of the smokestack. The plant, so this is still, so the plant stops, and here this is on a day when there is no wind. So you expect that the fumes will spread out and there will be a diffusion process going on. So we want to model this. All right, here we need to do some symbolic computation. If you are a little bit rusty with your calculus, don't worry, there is symbolic calculation, so there is SymPy. Here I use this to set up a plausible model for diffusion. So we take a decaying exponential in time. So in time we have the exponential minus t. And then we have also a cosine sitting in there, but now it's written as an exponential as well. Exponentials are very nice to use when you take derivatives, because the derivatives of the exponentials, they are themselves, but you have to know about the chain rule. So what could go wrong is actually that you forget the chain rule. So if you take the derivative with respect to this the t and the decaying exponential, you have a negative sign that pops in. Why the I? Well, the I, if you take the derivative twice, the I becomes actually also -1. So here we have a model where if we take the derivative with time once, that we get actually the same solution if you take the derivative of space twice. So this is what the slide essentially shows, a very simple interactive calculation with SymPy. Okay, so here is where we get to the decaying model. So if you remember, and we used this identity many times throughout the course when we considered signals and design of filters, we always had this exponentials coming in with imaginary arguments. Here, and then we could expand this as a cosine or as a sine function. So the cosine hill from there is actually not that far-fetched. So if you use that as a model for your initial concentration, then assuming to work with that plausible model of diffusion is not that bad. And we arrive at a very simplest example of the heat equation, or the equation of diffusion. So in a purely calculus way. So can we generalize this? Yes, we can. So we are in our air quality modeling problem. We are typically looking at the plane with the cosine hill. So let's consider the Laplacian operator then. So it's actually seen as the defined, so the Laplacian is applied to here a function in 3 variables. It just works in 2 variables as well, just drop the z. So in three variables, we have a function in three variables, and we dot the del operator with the gradient. So the gradient is denoted also with this del operator like. So that actually goes from the scalar field to the vector field. So applying this del operator gets you into the vector world. So I should probably have emphasized that a little bit more when I defined the del operator. And by applying the dot product, you go again from you go in the opposite direction. You go from the vector field back to the scalar field. And this Laplacian operator then allows us to write the heat equation in a very compact manner. So here you see the three-dimensional version of the heat equation with this Laplacian operator. Okay, so Laplacian operators are also useful if you look at the problem of edge detection. So we got at this by the convolution, but actually there is a much simpler way to do this if you look at the divided differences. And perhaps I should have defined what the divided differences are. You can find them in a numerical analysis textbook, so that's why I'll leave this here as an exercise. So look at the divided differences that we covered in MCS 471, so the precursor to this course. And then you will see that what you essentially are doing is that you are averaging, you are taking the differences between the current point and the neighboring points. So if there is, so we now have our picture as a matrix of grayscales. So if there is an edge, the edge is the difference between how should I say? So you have the regions of the same grayscale and regions of different grayscale. So this is what an edge is, the difference between two levels of grayscales. The Laplacian will actually pick that up. So applying this Laplacian operator to an image should actually show, is one way how you could detect the edges. Now, of course, you do this with the x and the y direction. If you have circular images, then polar coordinates might be a lot better to look at. So what is the Laplacian operator in polar coordinates is the third exercise. The textbook gives the Laplacian in spherical and cylindrical coordinates. So if you need inspiration for that, you can look it up also there. Okay. Now we are more than halfway in this lecture. And I'm almost done essentially, so I will not need that much time anymore. So let's now look at the air quality model again, the Advection Diffusion Equation, where we consider a profile of fumes, so high concentration at time 0, and then here in this picture there is no wind. At any time you see that the profile gets spread out. So we are transitioning now from a high to a low concentration that is modeled by this advection equation with now a non-zero right hand side. So if you forget the middle term, the derivative with respect to x, you actually have the heat equation or the equation of diffusion. So here we have the transport equation. If you look at the right hand side equals 0, so it's the transport equation with diffusion. So we have our concentration, our profile that travels, and that at the same time it is diffusing. Okay, so that is the model, the one-dimensional model. But might be fine for a first approximation, but the model can be quickly generalized so to the three-dimensional model, which involves a function in four variables for the concentration. I should have pointed out, and that was Balkan still pointed out, so you have the concave down geometric interpretation. So the constant k has to be positive. So in the very quick derivation of the heat equation, the constant was 1. So you can kind of intuitively see through the concavity of the solution, concave down, that k has to be positive. All right then. Here is now the general model. So we have the positive constant. The constant is replaced by a 3 by 3 matrix, and that matrix has to be positive definite. So that is a matrix that, if you compute its eigenvalues, then all eigenvalues will be positive. And there is still an initial concentration there. So this is the generalization to more dimensions of the advection diffusion equation. Okay, I'm done essentially with the material for the lecture, so in a little bit over half an hour. Can still stretch it for about 10 minutes, talking about 3 proposals for a project. So this lecture was following very much this chapter 2 of this industrial mathematics, this alternative textbook. Well, probably it's not an alternative for the way we like to run our courses, but it's also a course in real world problems. So what you should do there, so the chapter goes a lot farther than I was able to do with this introductory lecture. But on the other hand, we remember our heat equation, the Crank-Nicolson method, and the finite differences that we applied in MCS 471. In particular, for this project, use the difference methods, use the Crank-Nicolson scheme, where the stability was important. What is the step size in time and in space? So in MCS 471, we had code to run the method of Crank-Nicolson. So run the method of Crank-Nicolson, choosing the right discretization for space and time. So that is also discussed in the Friedman-Littmann book. Again, summarize the model. You should not repeat everything that is said in this lecture. It's mainly important that you can write it up in your own words. It would be good also to use the cosine hill as a profile. So the purpose of the project is going more towards the methods, to put the methods in practice in numerical analysis. In numerical analysis, in that course, we just started with the heat equation. That was the heat equation. We don't really care of any other equation, and we studied the methods. The advantage of this project is that now you see it in a practical, real-world problem applied. Okay, so then the heat equation. I kind of, with SymPy, with one slide, I gave a plausible proposed solution, just like with the advection equation. You propose a solution, and then you start taking derivatives, and that then gives the the partial differential equation. Now, the Wikipedia page is actually quite good and gives a derivation of Fick's second law. Work through that derivation, and it has a very nice illustration as well. So there is a computational visualization aspect. So try to visualize this. So this is then again with the so make an animation in sense, very similar to the previous proposal. You will have to use the uh, Jupyter notebooks and the codes, the Julia codes that we used in MCS 471. Um, the difference here again is that in this course, the presentations are at least half as important as the computations. All right, and then population modeling again. So I got this from our textbook. So we may be interested in modeling an age segment of the population. For example, that segment of the population that is old enough to work. So say between the ages 20 and 60. Um, how can you model that? So we have an age segment, so that is the space, and then we have, of course, the time. So the textbook, I give the page, offers a hint that this can be solved analytically. So you can eventually also start from a proposed solution and derive somehow that equation. So it's a little bit similar to the advection equation, but there is an extra term in there. Is this a model that is valuable? That is what is asked here. So in some sense, how do you model the population, the evolution of the population within a certain age bracket? Okay, so that's mostly it for me now. So in about 40 minutes, which is compared to the last lecture, not that dense. So this was an introductory lecture. Perhaps I still went a little bit too fast if this is your first encounter with partial differential equations. We derived the transport equation. Also, adding diffusion to this gave the advection diffusion equation. We will still get back to the transport equation when we study traffic flow in one of the later lectures. The purpose of this lecture is actually that you can find your way in the literature. So here we have our textbook, which solves many problems for many types of partial differential equations. We will see in later lectures still many examples. The air quality modeling problem comes from another course on industrial mathematics. And you're more than welcome to look through these sources. So as I indicated also earlier in the last lecture, even if you are not interested in any of these three projects, it is still very strongly recommended that you look back to the study. Now it would be a really good time to look at the section 8.1 of our numerical analysis textbook, or review your lecture notes, your notes from that course. In numerical analysis, we could only spend one meager week on solving partial differential equations. Here we have more time. So it's also already in the last end of the course, but I hope that here there will be a little bit more time to study partial differential equations. Okay, thank you for watching this lecture and for your interest in this topic.